Hey everybody, Dr. A here, and in this video we're going to be exploring an example of shear force and bending moment functions. So before we get started, I'd just like to remind everyone you need to write all of this down. Remember, this is not a spectator sport. In order to best understand this material, you need to write everything down and go along all the steps with me. So let's go ahead and get started. In our given information, we're being asked to write the shear force and bending moment functions for these two beams. Now, if you notice, both of these beams, beam A and beam B, are the same beam. We have a cantilever beam. As you can see, it's fixed at end A and it's free at end B. The span is 8 feet long and it's supporting a 2-kip point load at the free end and a bending moment, an applied bending moment or couple moment, you could call it, of 5 kip feet at the free end. And again, it's the same beam. So what's the difference between what we're being asked to do in part A versus part B? Well, the difference is where we're defining our location variable x. So in the first part, we're defining our origin as the fixed end, and our location variable x is pointing to the right from that fixed end origin at point A. Whereas at part B, our origin is defined at the free end, and our location variable x is pointing to the left, coming off of the origin at the free end B. So everything is the same except what we're defining as our origin and where we're pulling our location variable off from. Now, that's no problem. You can define your location variable and your origin wherever you want. The thing is, you just have to be consistent throughout all your steps as you're going through your analysis. So let's go ahead and write solution, and we're going to tackle part A first. So whenever you are writing your shear force and bending moment functions, all you're doing is you're using method of sections, okay? So you're using method of sections, which comes from earlier in statics, and you're making a cut section at a distance x away from your specified origin. Now, it's always good practice to you want to include the origin in the free body diagram of your method of sections process. So I'm going to make a note here. I'm going to say it is good practice to include the origin in your method of sections free body diagram that you're analyzing. So in part A, since our origin is at the fixed connection, we're going to use method of sections and we're going to make a cut somewhere along this domain of x, and our domain of x is going to be defined as x goes from 0 up to 8 feet, okay? So it's the entire span of the beam. And we're going to look at a left free body diagram when we do our method of sections process, and that free body diagram we're going to analyze is going to include that fixed connection A, which means we will need our external support reactions in order to do this properly. So for this part, we need external support reactions. All right. And again, that's because the method of sections free body diagram that we're going to look at is going to include the origin, which comes from that fixed connection at point A. So this is a pretty simple loading scenario. So I'm going to go ahead and draw a free body diagram of the entire beam. And we're going to have, of course, an AY. We're going to have an MA. And we have an AX, but we don't have anything applied in the X direction. So AX is clearly going to be 0. And we have our 2 kips at the free end. And we have our 5 kip feet at the free end, and then our total length is 8 feet. And so these reactions are pretty simple. You can probably just look at it and figure it out. If you have trouble looking at it and just seeing what the reactions are, write your equilibrium equations for the whole system and solve for them like you know how to do from earlier in statics. But by inspection, we can hopefully see that AY is 2 kips pointing up, and we can hopefully see that MA is 21 kip feet and that's going to be rotating counterclockwise, okay? So now we're ready to draw a free body diagram of our method of sections process, okay? So I'm going to say method of sections free body diagram, all right? And so we're looking at a left free body diagram, so we can include that origin, and we're going to draw on it AY, which is 2 kips, and we're going to draw on it MA, which is 21 kip feet. And remember, we're making a cut here. Now, where are we making this cut? Well, this cut is going to be made at arbitrary distance x. And when we make that cut, what's going to become visible here? Well, we're going to have a shear force that becomes visible, and we're going to have a moment that becomes visible. And remember, these are functions, okay? So this is going to be a function of x. V is a function of x, and m is a function of x. So make sure we know this is function notation, just like in math, okay? So it's not m times x or v times x, it's function notation. V is a function of x and m is a function of x. Well, now we're going to apply our equilibrium equations to this method of sections free body diagram, and we're going to be able to say that sum of the forces in the y direction equals 0, and we can clearly see that we have 2 kips minus v is a function of x equals 0, so v is a function of x equals 2 kips, and you can put a little sign there that indicates that it's going down. We assumed v as a function of x is pointing down. We did the calculations, it came out positive, thus it is pointing down. We're also going to say sum of the moments about the cut equals 0, counterclockwise is positive, and we're going to say 21 kip feet, and then we're going to say minus 2 kips times x, and then we're going to say plus m as a function of x equals 0. Now be careful here, this is 2 kips times x in this term, and then this is m as a function of x. So rearranging some of these terms, we're going to get m as a function of x equals 2x minus 21, and collectively this function carries units of kip feet, okay? So here are 2 functions, and that summarizes our complete answer for part A, right? That was part A with the origin taken as the fixed end at A. Now let's look at part B. Same beam, but we're defining our x variable and our origin on the opposite end, okay? So how is that going to affect what we're doing? Well, if anything, it's going to make our lives a little bit easier. So I'm going to make a note here. I'm going to say, since we will now analyze a right free body diagram that does not include external reactions, we do not need to solve for them, okay? So this is one advantage if you're able to define your own x variable in a problem. If there's not one given to you, you have to define one yourself. So if you can define an x variable that will avoid or bypass solving for external support reactions, that can save you some time. So here I'm going to draw a right free body diagram with my cut section shown here like so, and at the free end I have my 2 kips and I have my 5 kip feet, and what becomes visible at that cut? Well, I've got my internal shear force V as a function of x, and I have my bending moment M as a function of x, and I have a normal force as well, but that's going to be 0. And I'm going to draw my arbitrary distance coming from point B now, and that's going to be at a distance x. And so I'm going to follow a same kind of process I did before. Sum of the forces in the y direction equals 0, up is positive, and we're going to say V is a function of x minus 2 kips equals 0, so V is a function of x equals 2 kips, and we can show that as pointing up here. Now notice that's the same magnitude and opposite direction as what we saw for the shear force from part A. And then I'm going to say sum of the moments about the cut equals 0 counterclockwise positive. And I'm going to say negative 2 kips times x minus 5 kip feet and minus m as a function of x equals 0. So doing some simple rearranging, I get m as a function of x equals negative 2x minus 5, and that collectively carries units of kip feet. And these are my answers for part B. Now you might notice, you might be thinking, well, wait a second, this moment function that I just calculated in part B looks different than the moment function I calculated in part A. I thought we said we're going to get the same thing and it's the same beam. Well, physically the same thing is happening in both cases of part A and part B. The difference is, again, where we are establishing our origin and which direction we're taking as positive x. Okay, so if you think about it, physically it's still going to be the same thing. So let's do a quick little experiment. In the original beam, what would be the moment at the free end, for example? What's the moment at the free end? Well, let's look at our moment function from part A. At the free end, x equals 8 meters, right? So not meters, I'm sorry, watch my units, 8 feet. So if I plug in 8 feet in for x, I get 2 times 8 feet. 2 kips times 8 feet is 16, and I say 16 minus 21, and what do I get? I get a negative 5, okay? Now, what happens at the same point? Well, at the same point, which is the free end that I'm talking about, and part B, x is 0. So if I plug in 0 in the moment function for part B, what do I get? I still get negative 5 here, okay? So physically, the values of the moment become the same thing, and they become equal to each other, whether I'm using my functions from part A or part B. I'm just defining that x variable differently, so you have to plug in values of x accordingly based on where your origin is and what you're taking as positive. So hopefully you found this video helpful. If you like this video, please hit like and subscribe, and we'll catch you later. Thanks for watching.